Good afternoon, gentlemen. Today we will talk about structural safety or structural reliability, and this duration of 2 hours will just introduce the subject. We cannot go deep into it, so we will just introduce the subject of structural reliability to you. A ship has to withstand the loads coming onto it, and this capability to withstand we normally call resistance of the ship to withstand the loads. So there are two factors here, one is load, the other is resistance of the ship to withstand this load. If resistance is more than load, then of course the structure survives and there is no problem. On the other hand, if the resistance to withstand the load reduces, then the load takes over and there is failure of some sort. It may be a small crack, it may be a brittle fracture, it may be a major failure, or it may be a catastrophe like breaking of the ship into two. Why does this happen? If our conventional structural design philosophy is adequate, then we should have normally chosen a material and the sections, the ship section, in such a manner that it would have withstood the loads that come on the ship. Unfortunately, this does not happen, primarily because of the uncertainties associated with both load and resistance. Let us look at the loads that the ship experiences at sea and the uncertainties associated with it. Loads at sea and uncertainties associated with it. Let us see what are the loads that the ship experiences at sea. So, the one that you know very well by now is the so called static load, that is the load due to the distribution of weight and buoyancy. We assume here the ship as a longitudinal beam having small cross section compared to its length, and the forces acting on it are weight and buoyancy. Now, since we are aware of the ship geometry and also its structural distribution, we can calculate the weight and the buoyancy pretty accurately, and therefore, the shear force and bending moment experienced due to this loading can be calculated very accurately. Okay. Now, if I draw the load curve, you have all been acquainted with drawing of the weight curve, buoyancy curve and the load curve, which is the difference between the weight and buoyancy as along the length of the ship. Now, if I just draw a normal ship loaded fully and its shear force and bending moment diagram, it would look like the shear force would look something like this. Please correct me if I am wrong. Will it look like this? And the bending moment will look something like this. Is that okay? And this assumption is based on the ship being loaded up to a still water level, right. This is the shear force and bending moment curve when the ship is standing still in water. But when a wave passes the ship, the buoyancy distribution changes, the weight remaining same. Buoyancy distribution changes because the vessel may trim, may heel, and the wave crest and trough may be at different locations of the ship. So, if for an example we take a ship in a with a crest in the middle of the length of the ship, and the length of wave is same as that of the ship, let us take a wave which would look something like this, okay, with crest being in the middle and length of the wave is equal to length of the ship. How will this change? You can see what will happen. The buoyancy will increase in the middle and it will reduce at the ends, weight remaining same. Therefore, the bending moment will become more in the middle, because basically the loading will be more in the middle. So, if I draw the bending moment curve, the previous one was full curve, this will look something like this. This is the so called hogging condition bending moment, right. And just let us do the reverse, that is crest at the ends and trough in the middle, same equal length of the wave. Okay. So, if I draw it by a chain dotted line, it will be something like this. And how will this be? This will be just the other way. The bending moment in the middle will reduce because the buoyancy has come down drastically, and towards the ends it will increase, towards the places away from midship it will maximize itself. So, maybe typically it may look this is normally called the sagging bending moment. Can you see that? So, this is without taking any dynamic effects. The static load that we calculated, we can see will vary depending on the wave orientation on the along the length of the ship. Now, when a ship goes in a seaway, of course, this is not what happens. You do not have a wave equal to ship wavelength and poised either the crest in the middle or trough in the middle. We normally have a sea, a random sea, where there are a number of crests of shorter wavelength and varying heights. What I intend to impress upon you is that, therefore, the bending moment will not become, even the static bending moment at any instant of time will not remain as is shown by the full line here, but perhaps will vary somewhat between these two lines. Furthermore, during the life of the ship, if the ship experiences a damage of a compartment and load goes in, then there will be further complications, similar to what happens in the case of a unequal loading inside the ship. That is, if we have a ship and this is the forward peak bulkhead and this is the engine room forward bulkhead, maybe there are a number of holes here, something like this. It may be so that you are not loading all the holes. You may load some holes here. Let us take a typical example of holding these holes loading these two holes and these two holes and leaving this empty. You can well imagine what will happen. And if you are loading the ship fully to the full load condition, that means if we had the 5 holes loaded equally, the stowage factor would have been 1. When you are loading the same weight in 4 holes, the stowage factor is going to go up, go down, density will go up. Therefore, the loading in these holes will be more than what it would have been if it was loaded in all the 5 holes. Am I understood? And then what is going to happen to the shear force and bending moment curve? You can see here that the shear force will be maximum at these places, these locations. This is the shear force will become high here. Can you understand that? And therefore, there will be a change in bending moment. So, even the static bending moment, which forms the core of ship hull girder strength calculation, has a lot of uncertainties coming up with it, depending on various factors which are normally associated with ship operation. We have not talked of any abnormal situation. Normally, this is what is going to happen. Normally, the waves are going to cross the ship, and so on and so forth. So, you see, when I am talking of uncertainty, how even a very direct calculation value we are supposed to get keeps on varying. Then thermal load. Another type of static load that may come on the ship is thermal load, that is temperature gradient within the hull itself because of various liquids may be heated to different temperatures, and therefore, there may be a thermal load which is in the form of a static load. There is no dynamics in this. That also will work on the ship. Again, that is not a certain factor. What is the thermal load in terms of mechanical loading? It is difficult to estimate. It depends on the geometry, it depends on the quantity, it depends on the heat transfer coefficient, etc. Then you also will have concentrated loads such as experienced during dry docking. We are talking of static load. During dry docking, unlike in case when the vessel was floating and the buoyancy was giving you support, here you have the ship sitting on a few blocks. Therefore, the support that is coming is concentrated at fixed locations. The weight distribution remains constant. Whatever structural analysis you have done, you realize that this will change the pattern of shear force and bending moment distribution along the length of the ship. So, these are some of the variations you will meet while dealing with static load. Now, if we look at dynamic loading, dynamic loads, first let us talk of low frequency loads. First thing that comes to mind, of course, is the pressure variation on the hull surface due to distribution of weight. A ship is moving, sea waves are there, and because of undulation of the water surface and the motion of the ship, the pressure distribution around the hull, the hydrodynamic pressure distribution, which in a still water condition is equal to hydrostatic pressure at any one point. But when the ship is moving in a wave condition, the dynamic pressure changes from the static pressure the ship was experiencing, and this dynamic pressure keeps changing every instant of time because the sea condition itself keeps changing. Do you understand this? Do you know how the sea is represented? How will you represent the sea? how is the sea normally represented. Okay, from a captain's point of view, he would describe the sea by visual observation as calm, rippling, or rough, or so on and so forth. In this manner, in a literal word, he would like to define the sea. Whereas, if you had wind force measurement, then it would be, the sea would be defined as corresponding to a Beaufort scale wind speed. Scientifically, however, when we want to define the sea, we would normally take the wave height measurement at a particular point over a period of time, or at various points at a particular time. So, you get a space wise distribution of the wave heights as well as a time wise distribution of wave heights. This analysis would tell us what is the total energy content of the sea and how this energy is distributed over the various frequency ranges of the waves, assuming any sea, any random sea is a linear superposition of a number of sinusoidal waves. Okay, I think this part of description of the sea you will be dealing with in next semester. So, I will not go in details of this. But we understand that since the sea is random, that is, no description of this sea is repeated in nature. It means that as the ship passes, the ship encounters a different sea every instant of time, maybe having the same energy content as previous one, but basically the local distribution is different. Therefore, the local pressure generated, dynamic pressure generated around the ship is varying continuously. So, that is a low frequency variation, because the wave frequencies are generally much lower compared to ship's natural frequency of oscillation. On top of it, the ship itself is oscillating, that is pitching, heaving, rolling, etc. The oscillatory motions I am talking about, the heaving, the pitching and the rolling. So, what is happening every instant of time, because of the ship's oscillatory motion, its own orientation is changing with regard to the sea. So, like the sea wave changes the pressure around the ship, because of the ship's own orientation change, also there is a change of pressure. So, this also, because ship motion also is at low frequency, so this would also be a low frequency load. When the ship oscillates, you can understand any oscillatory motion, take any simple harmonic motion, acceleration keeps changing. And where is the acceleration maximum? At the end of the rotation. If I have a simple harmonic motion of a simple pendulum which goes this way, then comes back this way and comes back here, then the acceleration is maximum here at the ends, isn't it? So, when the ship is rolling, the acceleration becomes maximum at the end, and that acceleration is changing as the ship rolls. It's maximum at one end comes to 0, maximum at the other end comes to 0. So, it's continuously changing, and that creates inertial forces, mass into acceleration, very simple. So, this also is a changing force. So, the low frequency loads are due to the sea surface, variation of sea surface, variation of position, orientation of the ship, due to motion, and inertia forces due to acceleration. Understand that heaving also the same thing will happen, and pitching also the same thing will happen. Am I clear? Then what are the dynamic loads at high frequency or little higher frequency. These are all low frequency loads. Low frequency loads are generally large in magnitude. High frequency loads are generally low in magnitude, but it need not necessarily be so. High frequency loads, one of them we have seen yesterday. High frequency loads generally are regionalized or localized. Over the entire ship range, there are less high frequency loads. One we have seen yesterday, due to propeller. Yesterday we have seen this, yes, load due to propeller, the pressure impulse coming on the water due to the propeller action and ultimately going onto the ship's aft body. So, ship is being forced to this force due to propeller on hull, which we have seen, and you can understand the same will happen on appendages. A badly designed skeg propeller and rudder combination in a small vessel can create a large load on the aft body of the vessel, causing vibration which may be intolerable. Then, due to forces, the rotating machines, mainly the main engine. The main engine is sitting on the bed plates mounted on the engine side girders, and ultimately the load of the main engine is going to the ship. Now, the load of the main engine is not limited to the weight of the main engine alone. It is a reciprocal, it is a force generating machine. Therefore, the engine as it fires, the forces may be transmitted to the hull in a cyclic manner, maybe. Therefore, it is essential that the diesel engines are balanced properly, so that no resultant load comes on the, because of the firing of the cylinders, no resultant load comes. But then as we come to smaller and smaller engines, other engines, it may not be always fully balanced. And if we have other type, typically reciprocating engines, they are normally not, I do not know how you balance a reciprocating engine. You do not balance a reciprocating. So, there will be some forces coming onto the hull girder. Reciprocating engines and unbalanced diesel engines. This will give high frequency loads on the ship structure, again regionalized. Then you see, typically a naval vessel or smaller vessels which have large number of appendages.
Don't we mean reciprocation engines only?
Well, I was talking about reciprocating steam engines. Okay, diesel engines are generally balanced. That's why he separated them. Now, if we go for a naval vessel or smaller vessels, which may be twin screw, triple screw, and so on and so forth, there may be a large amount of appendages on the bottom of the ship, like bossings, struts, supports for the shafts of various forms, sonar domes, and many other things. If we do not take care at the proper design stage that the appendages are aligned in the direction of streamlines generated due to flow around the ship, then there is likelihood of generation of separated flow and vortex generation due to interaction between the hull and appendage, flow around the hull and flow around the appendage. And that will in turn induce high frequency forces on the body. Then sometimes, as I mentioned, okay, let me write it down. What did I say? Hydroelastic load, and then we have, as you mentioned, the sea as a combination of large number of sinusoids of low frequency. This is what I had said. But sometimes you get short crested multidirectional sea or confused sea, where there may be existence of short waves of high frequency, and this short wave frequency is not so low. It comes up, the frequency of short waves come up to the frequency of ship's frequency. So if such waves exist, which occurs sometimes, then you have got a resonance scenario where the short wave frequency and the ship natural frequency of vibration resonate. Then you have large amount of dynamic loads coming up, which is having a high frequency oscillation. This is normally called springing. And this affects the whole ship. So these dynamic loads these are dynamic loads of high frequency. Apart from this, you have impact loads, which apart from stressing the ship structure also cause vibration. Let us hear some of the impact loads. First in the mind, of course, is slamming. Do you understand slamming? Slamming is the ship's forefoot coming out of water here the forefoot has come out, then it comes back and hits the water. Okay, then what happens? If your ship has a flat bottom there, which would normally be so in case of a bulbous ship or in a U section shape, forward end, where you have a flat bottom, then the ship will get a very heavy impact with the water. As the relative distance between the ship and the sea surface becomes 0, there will be a large impact on the ship hull from the bottom. That is what is commonly called slamming. Instead, if I had a V section hull form, even though the distance becomes 0, it cuts through the water like a knife. So you can imagine that slamming will increase with today's modern ships, which are almost all of them are now bulbous bows or nearly fuller sections at the forward end, bottom. So slamming has become quite a major force to reckon with, and for this reason the classification societies take two measures. One, the forward end is strengthened so that it can withstand the slamming pressure, slamming force, and second, you impose a minimum forward draft so that the probability of slamming reduces. Do you understand? Okay. But all the same, slamming is there. It is a dynamic force causing impact and subsequent vibration of the forward body structure. Then impact of water on forward body, forward flare. If your forward section had a flare, then same thing will happen as the ship comes down. The flare, the bottom of the flared portion would have an impact. Is that clear? Right. Suppose you didn't have a flare, but you have large motions. Slamming is also not there, but the deck goes in water. Then the sea comes in. You understand? Green sea, does it lead to flare, impact? Does it lead to impact? Imagine this ship's forward end. The wave comes like this. There is an impact, isn't it? If the wave comes onto the ship and breaks on it. So, green sea on deck is another cause for impact loading. Then in naval vessels, you have weapons. Impact due to weapon effect, firing of a gun, the reactive force is also of impact nature. So, whenever you design a naval vessel, you have to be careful with regard to this impact load, the reaction force that comes from the firing of the gun or missile or whatever it is. Okay, these are some of the dynamic loads that come. A lot of dynamic loads are imposed on the vessel due to operation. What are the operations that cause dynamic loading? Typical will be if you are going through cold climate, ice load, either impact with the ice or ice formation on deck, these are all impact loads. Then you have impact with other vessels, a collision, right, grounding. But these are rare. Impact with other vessels, grounding, etc., rare phenomena. Can we think of something which occurs due to loading and unloading operation? Sorry? Along with, yes, impact against quayside. One loading which is pretty common, which stresses the vessel very much, typically in a bulk carrier, is cargo gear impact. Cargo gear operation and impact. That is, what does it mean? You have a load held on a grab and you drop it. That of course can be understood, it is coming on with the impact. Now the grab comes and catches the bulk. So that grab impact with the bottom. So these are some things which many times charterers are not very careful about, and it does affect the local strength characteristics of the vessel, and which may be translated to a global failure sometime later.
It's the hold also. Along with the cargo,
Yeah,
we are not able to control the crane. Who then hits the members also.
that's right. That's right.
The fast loading bulk carriers to shoot when we are loading.
To shoot the impact of the cargo on this thing, yes. This you said showed the picture. Who showed the picture yesterday? We had seen a picture yesterday that a ship had heeled to one side. You had shown because of faulty operation of ballast water at port. The ship has heeled. Whatever it has damaged to itself, it has also damaged the crane on the quay side. So that photograph was very interesting. But all this happens due to operational procedures. Then you have sloshing. Another load that is water coming onto one side and pressurizing that side, that is lossing because of oscillatory motion of the ship. Then in many vessels nowadays, including offshore structures, you have the helicopter deck or the aircraft deck. So, landing of aircraft, helicopter, etc. So, these are some of the examples of dynamic load coming due to operation, right. So, you can see my purpose of telling you all this is, you can now observe that the load which we think the ship should withstand is very indeterministic. You cannot decide what is the load the ship must withstand. The one that we are pretty sure about is static bending moment when the ship is stationary. That is the only thing we are sure through our calculation procedures. Then we take the wave bending moment. We can take the worst case scenario where the ship length is equal to wavelength, and we assume a wave height of L by 20 and do some calculations. That perhaps gives us an average what is the worst case due to wave loading in a static environment, but surely it does not take into account the dynamic effects, nor is it accurate enough to tell us, yes, this is the load that the ship experiences. So, the load itself is not very well defined. What about resistance? What about the material that you have taken, or you have assumed certain working stresses which this load should generate, and you have calculated the section modulus and said that the working stress is less than the yield stress or ultimate strength, whichever case it may be. How reliable is that? Is the resistance of the ship to withstand the load. Let us take material. First, let us take what are the characteristics. How will you determine the resistance of a structure to withstand a load? Let us see, what have you done? You have laid the structural members in a particular fashion, and you have said, taking the example of hull girder bending, you have said that the midship section modulus is the one that will withstand the load. The way you have calculated is right. Is this what you have done? And this is the one that is because of the material. Material means orientation of the material. Mind you, this is not material property, so this property is being generated due to the orientation of the material. If you change the orientation, this will change. What about this working should be less than, let us say, ultimate. Let us say at this stage ultimate, it can be yield strength or yield, let me put it also, it does not matter, depends on how you are looking at it. Therefore, this is the other factor which you are assuming as the basic material property, this and this. If these two are accurate, and thirdly this formulation, is this formulation accurate? Assumption? Is this an assumption?
No, that formula is accurate, but the calculation of bending moment is an assumption.
This formula is accurate? Does everybody say that?
For a beam, it is accurate formula.
Okay. Coming from beam theory, this formula should be accurate. But while deriving this formula, we have made certain assumptions, which very conveniently you don't wish to remember. Okay?
Simply same in tension and compression.
No. Let's see.
The radius of curvature is less.
Sorry?
Radius of curvature.
The very
Is low.
yes.
That's a fair enough assumption, except that what is low we don't define. Okay. But there are many other assumptions you have made. You have assumed that the beam is of constant cross section. Do you remember how this formula is derived? Anybody? No? Okay. It's important to remember how the formula is derived. Then you know what are the assumptions you have made. You have made some fundamental assumptions, which you will just realize from your experience on ships, which is not true. This one, that the beam should be prismatic or its cross section should be constant everywhere. This is not correct. Okay, number one. Number two, all transverse sections after bending remain straight. You remember that? If this is the beam, this is the neutral axis. All transverse sections, any transverse section that is here, should remain straight. It can only rotate. So now you have bent it. Let's say on one side we draw the bending. It is bent like this. Let's say. Then we assume that this end will become something like this. The section that was here will come here. It is still straight. It is not twisted. It's only turned. Isn't it a major assumption? What else we have assumed when you derive this formula? We assume there is no transverse effect, no Poisson effect. You know about Poisson ratio, the relationship of strain in the longitudinal direction to transverse direction. We assume while deriving this equation that there is no Poisson effect. Of course, later on we bring in a lot of complications and make a matrix form, but this equation on its own assumes that there is no Poisson effect. Another thing we also assume is the material behaves elastically. That is, if it is strained and the load is removed, it comes back to its original position. That means all elements which you have taken to calculation in our I by Y must not go into plastic region at all. There should be no deflection, no permanent deformation. Shear stress effects can be separated. We can calculate the bending stress separately and maybe then we can add up. That is, bending stress and shear stress can be calculated separately. All these assumptions are included in deriving this equation. So therefore, please understand what I am saying. These are assumptions which are not strictly valid. There are deviations from the assumption. When you deviate from the assumptions, your stress values will marginally change, the material value I by Y. Your calculation of Y and calculation of I by Y was based on these principles to be used in this formula. Am I understood? Yeah. Okay. So this is something you have to tell you how the calculations themselves bring in certain amount of uncertainty. The calculation, the procedure on the basis of which you calculate stress, the procedure itself has some assumptions, some inaccuracies, which brings in certain amount of uncertainty to the value that you have calculated, the stress you have calculated. It is not really that stress you have calculated, it is maybe plus minus 1%, 2%, something. Am I clear? Then, to make it more accurate, we do other calculations, like we do a finite element analysis. Ships are generally plated, so thin plates with thin stiffened plates. So you can do a more sophisticated analysis, assuming a load. But that sophisticated, when I say more sophisticated analysis, there is another assumption, that the analysis I was doing was not fully accurate. So I go for a more accurate method. But nowhere along the line I am saying this is the end of accuracy. That means there will be always another step which will be more accurate. So any calculation we do is inherently having some inaccuracy level, otherwise that calculation should be properly scientific and there should be no progress beyond that for that calculation. But as we know, the structural analysis principles, the stiffening, these assumptions that I made, modifying those assumptions, there are different calculation procedures, and all calculation procedures, particularly the numerical calculation procedures, are associated with certain amount of assumptions and inaccuracies. So that will reflect on our stress calculation. Let us look at the material, steel, very well known material, all properties are known. If all properties are known, why do the classification societies give a chemical composition? Or can anybody guarantee that all materials that come out of the steel mills have the chemical composition they are supposed to have? You can take a sample, you can test a sample. Normally, if you look at the class rules, it says composition of particular material should be minimum so much or maximum so much, but it never says it will be this value. Do you understand? Carbon content should be less than 0.5%. It does not say 0.5% means 0.49 or 48 or 47. All of this is acceptable. So what I am trying to tell you is that even though steel making is a very standard process and you can control the impurities in steel very accurately, even then there is always a small amount of inaccuracy in the chemical composition and in rolling the plate. When you bring the steel plate out, say 10 millimeter plate, would you get exactly 10 millimeter? It would again vary within maybe 2%, 3%, 5% depending on the rolling mill. You will have a variation of thickness all along the plate surface. Am I clear? Then you bring that plate. Let us see what is the history of the plate. We bring that plate through a transportation process. Do we make sure that the plate does not bang anywhere? It is handled very carefully, or do we build up stresses while handling? We do not know that. So there is a little bit of, however small it is, a little bit of uncertainty is there in the mechanical property of the steel itself. Then it comes to shipyard. It goes to the store, gets stored. When it gets stored, what happens to it? First, a corrosive layer forms on top of it, because normally all shipyards are in climates which are moist, and so it stays there. So how much corrosion takes place will depend on the length of time the plate is in the yard. If I take the plate out quickly, then corrosion has not set in, but if the plate has been there for 6 months, then there could be some amount of corrosion. So, you have a corrosion layer on steel on both sides, you bring it out, you go to the rolling mill which removes the corrosion and then painting. By this time the thickness has again slightly reduced, mind you. Then you give a primer and it goes to the hull shop, prefabrication shop, etc., and finally to the ship. Why do you paint the ship once again when the ship is almost ready for delivery? You paint it, at least the outer surface, because you expect that the initial coat of paint that you have given might have peeled off, there might have been some corrosion, ship might have the plates might have become rough. So, you want to give it a full coat of paint so that she is ready to go to sea. So, which means there is a degradation of plate properties all across the building process. The degradation may be more based on the length of time it has been processed, length of time it has been stored, and environmental conditions. Painting method, how well the plate has been painted in the first stage and how it is going to be painted at the last stage, whether the plate is being sandblasted and painted or only painted. It will depend on so many factors, but basically the material property will change. Yeah.
After the completion of the units itself, one red oxide coat is again introduced.
I am not aware of that, maybe in naval vessels, not in merchant vessels. Okay, whatever it is, still some time is spent. We get the point that there is a possibility of some little degradation due to handling of the material and storage of the material in the process of production itself. Okay, this is for the new plate when the new ship we are considering. The plate properties have changed slightly. This part has changed slightly. This has changed, and we have seen the load reflected in bending moment. That uncertainty we have seen. We will stop here and we will do it in the next lecture, the remaining part. Thank you.